Okay, again, thank you very much for giving me this chance to talk about this material. Because it's a two-part talk, just like TV series, I'll like to do a review of basically what happened in the last episode, and particularly because there are some technicalities, some definitions, some theorems, and then we move on to new material. So we did talk about tightness and solidity, but not about internal categoricity. When it comes to tightness and solidity, basically the motivation to study them was this result of Albert, that if you take any two extensions of Peano arithmetic in the same language as Peano arithmetic, and by extension, I mean theories that are closed under deduction. So by theory, we mean we have closed them under deductions. Then if you use a retract of V, and think of that statement as basically half of what it means to be bi-interpretable, then V is a subset of U. And then in particular, if U and V are bi-interpretable, then U is actually equal to V. So bi-interpretability for extensions of PA coincides with equality. So it's a remarkable property that PA has. And that we call tightness. So tightness of a theory is basically what this last line is indicating. Now, we reviewed some basic notions of what it means to be interpretable, and which I will not review. Let's just move. Oh, let's look at retract actually. So retract was defined here. So to be a retract, you have to have, first of all, mutual interpretability at work. You need an interpretation of U into V and V into U. These are called I and J, such that, and also one other item, you need also a binary formula, capital F, which is right here, such that if you begin with any model of U, take the one interpretation and then the other interpretation, then you almost come back to the same place, almost in the sense that isomorphism. But
Ali, so yes. Since you're reviewing, I was thinking about something to ask last time, but
sure.
Look, so because it's always interesting, this whole when these notions like what you have on this slide, you know, some theories are tight and some are not. Yeah. And this particular Albert's result about PA, I understand that from the proof that it has something to do with the fact that, you know, this by interpretability give you the mutual embeddings as initial segments.
Yes.
So this in particular, so to have some comparison with other theories, you need something that already the idea of end extension plays a role, and that certain chunks of the theory are preserved by those extensions necessarily if they go both ways.
Actually, what you said was correct about Albert's, summary of Albert's strategy. But when it comes to proof of tightness of ZF, for example,
right,
end extensions will not help us.
I see.
It's going to be a very different proof actually than, and it's going to be much more work involved to prove the tightness of ZF.
Oh, I see. Because okay,
yeah.
So
yeah, basically because ZF could easily interpret a model of itself, and it is true that other model would have to be an omega end extension, but it not need to be an end extension. Meaning, if a model of set theory interprets another model of set theory, the omega of the other model being interpreted would have to be an end extension of the model that is doing
right.
it. But the whole model need not be, and often is not.
Yeah, but in general, the situation that the theory really has to be such that if one model embeds into another, then it already has some, you know,
yeah, I guess it's in this definable way. So what's really important is that you're embedding not externally, but basically the model can verify.
Right,
yeah,
right.
And that when you iterate this these embeddings, again, the model can verify that what you do, what you get by iteration. This is this M, J, and then I is the result of iterating the
right, because at the end you and Mateusz, you're talking about this open problem about
right. So it turns out, yeah, let's look. Thank you. Yes, let's just go back to, I guess that was the picture, but yeah, let me just wait for one few seconds before we get to the open problem. So the point of the so it's kind of a big deal that retract is not quite being bi-interpretable, because it turns out to show that PA is tight or a theory is tight is usually a little easier than to show that it's solid. So solidity is this property that I like to focus on because it's more model theoretic and it's also easier to. So this is the picture of retract right now. I guess we haven't gotten to solidity yet. Let's see. Let's go back to. Okay, here we go. So solidity basically is a strengthening of tightness in the sense that it easily implies tightness. So, and that now I can talk about that open problem. And it basically says if you have three models, M, M star, and N of the same theory, T. So T is said to be solid if starting with a situation where you have these three models where M interprets N and then N interprets M star. And also, you furthermore know that the beginning.
And a very quick question. So, sorry to put it down. Sure. Did you invert your inclusions this time, or you keep the same notation as last time? Because original definition.
No, no. These are all. Let me actually slow down. So
the same as last week.
So I have corrected the typo. So this actually says M interprets N. So the first model interprets the second model. So it's larger than or equal to basically means it's able to see the other model. So M can define the universe of discourse and the operations of N, and the same thing with N and M star. And of course, because when you iterate interpretations, you get also an interpretation. So M can also see M star because M can see N and N can see M star. So, so we have these two interpretations basically at work right now from M to N and then N to M star. And also the beginning model that is doing all this interpretation can see that M star is isomorphic to itself. There's a definable map in the sense of M that M can see, actually, there's a copy of me if I just follow the two interpretations. If this happens, then M should also be able to see that it's isomorphic to the middle model. So this is solidity, that you cannot squeeze a model that is not isomorphic in a definable way to the beginning model if the beginning and the end models are isomorphic. So this is solidity. And the proof of solidity of PA is, we saw the proof of it. It easily implies tightness. I mean, meaning if you just look at this definition and say, if I know that T is solid, is T tight, then it's just basically, this definition tells you that every model of, let's come down here. Let's remember the definition of tightness. So if you give me a U and V, and they're both extensions of T, and if you tell me that they're also bi-interpretable, then I'll be able to, just looking at this property of solidity, know that every model of U is a model of V and vice versa. And therefore U is equal to V by the completeness theorem. And typically a proof of tightness of a theory is a bit easier. Sorry, the proof of tightness is a little bit easier than the proof of solidity. And conversely, the proof of failure of tightness is a little bit harder, meaning you have to work a little harder than failure of solidity. But abstractly, and so here's the situation. If you just ignore neatness for a second, that's just for bookkeeping purposes. The implication solidity implies tightness. I introduced this definition, to be honest, just because I was interested in this property of solidity as a quick way of getting tightness. But then, of course, a natural problem arises. Does the arrow reverse? And so that's the question. For all of the natural theories we've looked at, the arrow does reverse, meaning the natural theories we found to be tight, they're also solid. So if there's a counterexample to this implication, solid implies tightness, it would have to be kind of a strange counterexample, kind of unfamiliar, not within the domain of probably familiar theories of arithmetic or set theory. And it could be, for that matter, it could be really an easy one, easy in the sense that it need not be exotic. It's just that, to be honest, I didn't neither. Okay, so I did think about it a little bit, and I talked with Mateusz for some time. We played with some theories, and And we did manage actually to come up with an example where the arrow didn't reverse, but the interpretations were two-dimensional, and the theory at work was dense linear orders. And so that's kind of the summary of the situation. It's an interesting problem, but it's really not an important problem because of what I just was summarizing in terms of the natural theories that we meet. Okay. Also, it's easy to check that solidity and tightness are preserved under Bai interpretations. Bai interpretations preserve a lot of interesting natural properties of theories. Actually, I was just reminded last week when we talked about stability considerations that Shicherba already noticed in his paper, the old paper from 1980, I think, that Adam was asking me about, that omega categoricity is preserved by interpretations, but then there is some work that he referred to that showed that uncountable categoricity is not, not by interpretation, but let me just actually not pursue that line, because Shicherba is not talking about by interpretations, he's talking about interpretations. And so his remark, the remark I'm making is that there's a distinction between preservation of stability, which is true under interpretations, and preservation of categoricity. For omega categoricity, things are okay. For uncountable categoricity, as pointed by Shicherba, they're not. But that's a completely side comment. So the solidity of PA, the basic idea was that
Ali,
yes, of course.
I wanted to ask a couple of slides ago about the well,
Sure.
It's okay if you don't go about it, but I wanted to ask about retracts. Is there, so I guess this is along the same lines of this question of whether tightness sort of the implications reverse. Is there an example? So my understanding is by interpretation is kind of like U is a retract of V and V is a retract of U, but in a way, in a uniform way.
Yes, the same I and J, yeah,
right.
That's right.
And so is it possible for U to be a retract of V and V to be a retract of U, but for U and V to not be bi-interpretable?
I don't have an example in my pocket, but these questions are exactly what's actually studied by Albert in his paper and then in later papers. So I cannot tell you of a natural theory where that happens.
Okay.
But overtly, certainly, I'm pretty sure that I've seen an example of it, but I won't be able to point to it given. It's in one of Albert's papers or another paper which I'll try to actually track this down. I mean, not write a note to myself because that's
before you leave this slide.
Yeah.
Before, because it's got almost all the information except for one thing, but I mean, just remind me of the notation. Who's interpreting whom, and which way is I going? Who's okay? So U is on the left.
Yeah, U is on the left, and this situation here, U being the bigger item because of the way the triangle is standing. So right. U is doing the interpreting. Models of U are doing the interpreting of models of V.
Models of U are doing the interpreting of models of V. Okay, right?
Yeah.
Yes.
Yeah. So you begin with any model.
That's what the bigger, right?
Yeah. And that's why, this arrow starting with this box is of all models of U right now. So I went to a typical model of U, and then I looked at the interpretation at work, and then M says, oh, I can think of a model of V. This N is a model of V now being in this box.
Right, and then the other component is an interpretation the other way around. So there, V thinks it's bigger somehow.
Yes, exactly.
V is supplying the raw material for the models, and it's going back.
Exactly.
Okay.
Exactly.
Okay. But the upshot is that you're doing the composition over there in the world of U.
Precisely. The composition is
so that's
being
the
done.
setup, and then to say that you have a retract is there's this plus some containment. So which way, right?
Right. So the containment has to do with the fact that when you to be a retract is exactly that there's an I and a J, and also this F here is important, that when you do the composition, there is a definable map that that U knows about.
Wasn't there something, or maybe that was your definition of neat or something, where it was
Yeah, that's
like,
the definition
like
of
hypothesis, if something is a retract, then, and it's in the same language, then you have like an actual on a set theory containment. So who was containing who?
Oh,
in
yeah,
that
yeah. In this picture, I can show you.
Yeah,
if
yeah,
you
because
think
that
of,
was like just
yeah.
keeping the two straight. I could
Yeah,
not
yeah, yeah.
do.
If you want to think about solidity, solidity basically says if you have this picture, then U is solid if you if
It's about you being solid. Okay.
yeah. So U is solid if you basically are if you also know that this N is a model of U. So basically in this situation,
Oh, model of view and possibly more.
yes, exactly.
Right.
Yeah.
Okay.
Yeah.
Right. Yeah.
Yeah. Then this middle model, this N, would have to be isomorphic to M. That's how meaning M would have to say, oh, this middle one is actually isomorphic to me. It's not really different from me. Meaning if you want to look at the symbols, because in the symbols it also looks
Yeah.
You have two interpretations, I and J, and you have this formula F. Oops, sorry, this was I meant to go here. There we go. So if M is doing the interpreting, and in this case, they're all models of the same theory, T that we're saying is solid. So M thinks of a model of N of the same theory, and M star of the same theory, and M knows there's an isomorphism between the last model and itself. Then that middle model will have to be isomorphic to M. So somehow in this inequality version, think of it this way. If you think of this as literal inequality, M greater than or equal to N greater than or equal to M star would say that M is, and then M star is equal to M because we're saying they're isomorphic. Says that M would have to be equal to N. If you think of equality as defined.
Can I ask a really pedantic question here? Just this shows my inexperience, right? So obviously this is definition of the meta theory. You're quantifying your existence an isomorphism, right? Do we or don't we care that the M definable isomorphism I is effectively determined or effectively determinable from I0, or is that yet another distinction? Or I mean, maybe it's true in all examples, but
no, actually, right. So the way this I is born is because it's supposed to work through all theories. The way it typically works is that it takes the information I0, but it also takes the information that is implicit here, basically the information of how was N interpreted and how was M star interpreted. So it takes this 3 data points, this I0, and then these interpretations, and then
all that is sufficiently definite to build.
Yeah, to build
it's an actual recipe. It's like saying the Schroeder-Bernstein theorem is a recipe.
Yes, exactly. It's a recipe. Yeah. Meaning, in all the cases we look at, there's a recipe, and you could even put that into the definition.
Oh, okay. Well, that's what I was wondering. That's what I was wondering. I kind of figured in all cases that was because how in the world else would you recognize it without some utterly bizarre version of choice? But yet I just don't know. I actually don't really have an opinion in terms of like the pedagogy of setting out the theory. What makes more sense? What do you think? What's customary in these cases? I'm just leery when I teach something about saying when I say there exists a form existence of non-first class objects, right? What am I actually talking about? That's why I say it's pedantic. I shouldn't be interrupting, but I've been thinking about this all day in my homework set, right?
So this definition, I would say, is very, very satisfying to people who just do model theory as opposed to proof theory,
right? Because
it just tells you exactly what happens at the point-by-point model level, and that meaning this definition does allow. If you change these 3 models to another triple for this formula defining I to be different, but looking at in a way,
for all we know, I mean, there may well be an I hat that also, like the Schroeder-Bernstein theorem, right? There's, you could do it quite right. I mean, you're not necessarily claiming anything canonical here.
That's right.
Although maybe in practice it is.
Actually, in many instances it is actually, yes. Yeah.
So I guess this is all written up in your paper. I should look at it more closely.
Yes,
but
yes,
I mean, it's, to see the actual formula, because it's really about here is the way to do it.
Yeah. Actually, the point that you just made about its uniqueness is the fact that there's just really in practice there's one M definable. It in a way hooks up with the heart of the proof of solidity of not PA, which we saw last time, but the solidity of second order arithmetic. And I just want to let me just look at this picture for a second. We'll come back. This picture, the only thing I want to say about this picture is that the solidity of second order arithmetic, if you were to just summarize it in something that you just write as some sort of telegraphic message, it has to do with the fact that there is no definable non-trivial automorphism of a model of arithmetic, as opposed to for Peano arithmetic, which was there is no definable cut in a model of Peano arithmetic. In a model of second order arithmetic, there's certainly no definable cut, but that's not going to be sufficient for getting the job done. We need also at some point to take advantage of the fact that if you have a definable automorphism of the universe, then it sends everything to itself basically and you do this by this induction, of course, argument that is available. So this is basically what gives you the uniqueness at the end, that there's just one way of hooking up that isomorphism. Let me, at this point, also go to one other item that let's see, just making sure I didn't shortchange you. Yeah. So in this diagram, or rather page, I just wanted to bring your attention to, because we went over it fast. Again, we're going to do it fast this time, but I'm going to do different fast things this time. So this theory, ZF without infinity plus TC, TC stands for every set has a transitive closure. So this theory is a sub-theory of finite set theory. So finite set theory, ZF sub fin, which I don't have on this page, but ZF sub fin would be exactly this theory plus the negation of the actual infinity. The way it stands right now, this is a sub-theory of both ZF and also finite set theory, because you simply take the infinity axiom out as opposed to replacing it with this negation. So this theory basically can also be proved to be solid. Now, why is this a big deal? Because this is a sub-theory of ZF fin. ZF fin is bi-interpretable with PA. I have this conjecture that PA is in a way minimally solid. So you would think this would show that PA is not minimally solid, because this is a sub-theory of a theory bi-interpretable with PA, namely finite set theory, and it is solid. So we're looking at a sub-theory of a proper sub-theory of a theory bi-interpretable with PA, which is solid. So it turns out it is seemingly a contradiction or solves the problem or whatnot, but it turns out minimality is not going to work here. Meaning is the conjecture that PA is minimally solid does not translate to the equivalence that ZF fin is minimally solid. So being minimally solid is not preserved by
change of signature and
by
all this
change of signature. Exactly. Yeah.
I'm just wondering. I mean, I was going to ask. I suppose the answer is no for the same reason, but I was wondering, would there be a way? Because I read this K1, but that's actually how I got interested in all of this years ago, right? But I mean, if you take, all right, so the actual equivalence, if you will, is with ZF minus ZF fin plus TC and PA. Right. So is there could there be an identical fragment of PA that corresponds to just ZF fin, or is that it just doesn't
no,
work
no, actually it doesn't work that way. So that's actually
too coarse. Interpretability is too coarse. It's sort of the same. That's kind of what I was thinking, because I would have been aware of it, I would think.
Yes. Yes, that's exactly what is at work here, that there is no corresponding subtheory of Peano arithmetic that corresponds to basically ZF fin without adding the TC. Just oh, by the way, the proof of this fact, the fact that this theory is solid, it actually, you need to know not only the way that you work the proof is not only you would take advantage of the fact that PA is solid and also ZF is solid, but you have to also show, if you want to do the proof right, that no model of PA is bi-interpretable with the model of, or even a retract of a model of ZF. Let me repeat, no model of PA is a retract of a model of ZF, and no model of ZF is a retract of a model of ZF. So it's actually, this in the paper I'm writing up, but what I'm saying is that it involves more than just putting the solidity of ZF and the solidity of PA together. But those two are the worst.
And these things, for example, wouldn't be true or might not be true if it was just Zermelo rather than ZF.
Thank you. So the failure of solidity of Zermelo was shown in a joint paper by Hampkins and Frary.
Oh, yeah, right. Yeah.
Just about maybe 2 years ago or last year. So
I guess that's why I'm asking. Yeah.
Yeah. So they also show
that's a very interesting model they look at, the one from Adrian's paper.
Yes.
With the growth rate and
yes. It's a very nice construction. It's also known that if you draw a power set, they showed that in their paper with another argument, that if you draw a power set, again, solidity fails.
I'm more of a replacement denier than a power set denier, but yes, I did look at that.
Yes, okay.
I've been accused by many people of being a replacement denier.
So let's see. Then this Tarski arithmetic this is a theory in basically PA star where you add a predicate and you add induction for that predicate, but you also have to say more. You have to say this predicate is the truth predicate. This can be iterated, by the way. You could also have like double Tarski arithmetic. You could have another predicate which is the truth predicate for this model basically, and that would be also. You can show this solid. You can kind of iterate it. It's kind of similar to what happens when you go from PA to Z2 or from Z2 to ZF. Meaning there are different. These solid theories, in a way, are natural stopping places. We don't have any class. It's too early to have a classification theorem, but this is the sense one gets that there are this natural stopping places in the foundational theory. Okay, now finally, after all that. Let's look at how this connects up to von Anden's notion of internal categoricity. So in a series of papers, von Anden has shown that both PA and ZF are internally categorical. I'm going to give you the definition and of what it means to be internal and categorical. But let's see. Before we do that, I just wanted to point out that the proofs of internal categoricity of PA and ZFC. So actually, Yoko in his paper uses ZFC, but it turns out the proof can be carried out for ZF. So that's just a little, I put it there because his papers mention ZFC, but you could do it with ZF and still the theorem goes through. But the point is that the proofs are pretty similar to the proof of solidity of PA and ZF, but they're, meaning when you eyeball them and you look at the flow of the argument, you could see that both proofs are pretty much doing many of the same things. But interestingly, when it comes for ZF, not for PA, the proof of solidity of ZF, at least the ones that we know of, there might be one which bypasses that, appeal to Tarski's undefinability of truth, which is absent in the proof of internal categoricity. So that at the intuitive level says that probably this is a weaker notion. And at some level, solidity is a stronger notion because it takes a little more ingredient to establish it than internal categoricity. Now, I'll say more about that. So let's look at the official definition of what it means for PA to be internally categorical. So what we do is that we take two disjoint copies of Language of Arithmetic. In the slides, I have a red copy and a blue copy. In the paper is a subscript 1 and subscript 2, meaning in Yoko's paper. Then you consider a theory which I call PA double. I don't think pardon me, Yoko has a name for it, but it's basically the red PA parentheses, the blue copy of PA, and the blue PA parentheses, the other colored copy. The idea being that a model of double arithmetic, double PA, looks like basically M with two versions of plus and two versions of time. And this part of the axioms basically say that that the blue version acts like the extra predicates and still induction holds for them. So the axioms of PA, for example, if you think about Q, so the axioms of Robinson's arithmetic hold for the red version. And then in the induction, you could use any formula involving any of these four operations. So that's basically.
Okay, can we say this again? So, I mean, because your color coding here has a lot of information, and I mean, it's meant to. I want to get this right. So, the part that just says the PA without the language, the color there refers to the base. You have your two base symbols.
Yes.
No, you have your four symbols, and they come in two colors, two suits or whatever.
Yes.
And which suits are the base play the base role of the language, meaning they're the ones. As you say, the Robinson arithmetic.
Yeah. So the base is right there, and the extra predicates you could use the induction. You can not only use the red base in the induction, but also the blue stuff. So what goes in the?
I see, but the blue stuff just simply isn't mentioned in the base. They're just treated.
That's right. They're not mentioned in the base. That's right.
But do we assume the Robinson properties of those?
We assume them in this part. So that's why we add also this one. So.
But then in that part you unassume them from the other. So you never actually. But you recover some of them, right? Don't you recover things like commutativity?
So if you suppose we only had this part, so this part basically, we just had half of this theory. This part would say that the red plus and times are just basically very well behaved arithmetically, but and that the blue part can be used in induction, but doesn't give you any idea about what is the blue part really doing, because it doesn't have any axioms about the blue part except that.
So we don't get things like commutativity and associativity from the blue part. Okay, I was mistaken. I was thinking about something else.
Yeah.
You assume nothing about. You don't even assume distributivity.
Exactly nothing. Yeah. They can just participate in the induction axiom, but they don't have any base to start with. So we don't know. In this theory, we don't know that, for example, that plus is commutative, because. All
right. So you do that, and then you do the mirror image on the other side, and then you take the union out. Am I supposed to think that there could be potentially weird interactions coming up in this union? Am I supposed to hold? Is this all about?
No, I think that's why we took disjoint copies so that
they're all right.
Yeah.
Okay. So I don't want to think of it that way. Okay, good.
Yeah. And then and
that's
basically
a strange thing to do.
So let me ask you. So maybe to help with this is very helpful, Adam. But can we think something like you start with this M with red plus and times, and then you somehow make some automorphic copies. Keep addition and do something with multiplication to make it a little bit different.
Sure.
And that would be model of a PA double.
Yeah, exactly. Meaning the language being disjoint doesn't preclude us from basically defining. You're right. Maybe this blue plus in a model of PA double, maybe this plus is the same as the old plus, and that this multiplication has been altered.
Okay.
Or vice versa.
They doesn't have to be. They could have both been altered.
That's right. They basically can be completely altered. Yeah.
Oh, I see. So once you take the union, these things that I was asking about partly go away, because you do get the Robinson axioms on both sides, but only because you took the union.
Yes, exactly. Yeah.
Right.
Would it be sufficient to just add the Robinson axioms to red PA, blue LPA to get the double, or?
Yes. In this PA part, we could just do, let's see. we will get, so the idea is that, yeah, I think you're right. I think if we just replace it with Q, a red version of Q and a blue version of Q, the main point is that we will get the basic beginning, the way plus and times should start to begin with, which Q would give us. And then induction mentioning both L of PA. So maybe the point of this parenthesis, maybe as long as going back to what Zach is asking. So this L of PA basically says you can not only use induction. Oh yeah, so Zach, I think you cannot do it because so this L of PA, when we add it, it means you can use induction not only using the red symbols, but also the blue symbols. So you need to be able to have instances of induction where blue and red are both present. So with that understanding,
Sorry, you need to have for what purpose? I missed the beginning of that.
So basically, you want to be able to have the red operations and the blue operations interact, right? To be able to see it, basically that we get an isomorphism between these structures, the blue. So and
in fact, the induction scheme on both sides is actually the same.
Right. Yeah, you want induction.
It's like literally the same inductions. It's just that you have different base.
Yeah. I think, yeah, Zach was asking if this PA can be replaced by Q, and then we have Q parentheses. But I think this notation wouldn't make sense because usually we write a schematic theory parentheses an extended language. So Q parentheses something is not usually. It's kind of a misformation because so PA, we know what PA is, and then PA parentheses X, which is same as PA star, says, okay, now allow X to be participating in the induction axiom. The same thing with ZF parentheses X.
Right. Yeah. Kind of a follow-up on that last question is, if you have this, sorry, and so I'm annotating, sorry. So if you have this, that gives you the induction, that extends the induction from the red to the blue, but then you replaced the other side with just Q for
okay, yes.
I meant I should have fixed. I could have done that in blue. Yeah, I meant for that to be in blue. Right.
Yes,
if you just so if you don't have this extra induction scheme on the right hand side, and you just have the algebra axioms, the basic,
right. Yes.
ring axioms or semi-ring axioms.
Yes. So to summarize what Attar is saying, if we keep this the way it is, in this way we have induction both in blue and red together at any time is needed. Then we just need to add a blue copy of blue Q here, and we don't even have to put this extra parentheses. I guess this notation, the way it stands, it kind of keeps the symmetry between the two. But as Attar is pointing out, this part can be just replaced by a blue Q, as he just has done here in this diagram. Yeah. So we're now on the same page. So that's pretty much the essence of what Zach was pointing to, that this can be reduced without losing any power by, at least in one instance here, replacing PA with Q. So let's see. So the categoricity theorem basically says that if you have a model of this theory, then the model can define there's a definable isomorphism between the blue arithmetic and the red arithmetic. So that's the internal categoricity theorem of PA. And you can imagine the same kind of thing would happen for ZF. You have a red epsilon and a blue epsilon, and pretty much you have a similar theorem there. The proof for arithmetic is much simpler than the proof for set theory. And the proof for arithmetic, if you haven't seen this before, it's a great exercise to see it, because
do you have to, is there anything fiddly, like you have to declare the same constants? I mean, what's the signature here? Are 0 and 1?
Oh yeah, so at this point, no, the signature,
or do there exists 0 then 1? I mean, how are you formulating?
The signature actually could be just exactly what I had. You can just have plus and times.
That's also how I'm formulating group theory in my set theory.
Yeah, because basically all the other stuff can be defined from plus and times. Yeah. But usually, you're right. In many books or
You might,
texts,
it might be more restrict. I haven't done the little exercise, like, you know, like when you formulate group theory, the fact that the identity is unique, you know, you could give yourself less and then prove that as an exercise. So I don't know if that's the situation here or not.
well, right. I guess if you
Care.
define 0 as the identity element, then you have to prove it's unique. You're right.
Yeah.
By induction. Yeah.
But you do have induction. Yeah. Okay.
So, so I hadn't looked at in my 2016 paper. I don't think at that point I was even aware of Yoko's work, Yoko Vanonen's work on internal categoricity. But when Hampkins and Frey wrote their paper, which came out, as I said, a year or two ago, Freire, I guess I should say, that's the Portuguese pronunciation. They gave a soft argument that the internal categoricity of ZF implies the tightness of ZF, not the solidity. As I was saying, solidity takes a little bit more work, but it implies the tightness of ZF. And their proof strategy also works for PA. So if you have internal categoricity of PA as a theorem, you could just by a soft argument get tightness of PA. And the proof, this implication I'm referring to is much simpler for PA than for ZF. So this would be also a good exercise. But I want to say more. I want to basically, it turns out the proof of solidity of PA and ZF actually show a stronger property that I call G solidity, a G for generalized. And for G solidity, basically, we look at models of PA star, PA in an extended language. So this is the definition of what it means for PA to be G solid. It means if you have 3 models, M plus, which is a model of PA with some extra relations or predicates or functions or whatever you want. And the same thing with N plus, you have a model of arithmetic. And these dot dots don't have to be the same. So these dot dots here and these dot dots here don't have to be the same. And you have also a model K. This should have been K plus. So we have M plus, N plus, and K plus. And the reason I'm using plus is so I can refer to the arithmetical part, the model of PA part, plus some extra garbage.
So you're refining the structure in potentially different ways. Like maybe the underlying set is like PA, but like on the one hand you're doing second order arithmetic, and on the other hand you're doing, you know, some other cockamamie thing, and you're not requiring those signatures to correspond.
Yes.
That's what you meant by that.
Yes, exactly.
Okay, and there's no plus in the last one. Is that a typo or do I care?
Yeah, so this was a typo on my part. This should have been also, this whole thing should be called K plus. So this K plus, which appears here, is just shorthand for a model of PA plus some extra garbage. Yeah. But the important thing is that this is what I'm calling extra garbage. They are all models of PA garbage. So meaning they all satisfy PA in their own extended language. So this satisfies PA in the extended language. The same thing for this model, the same thing with the third model. And if you have this situation, and if you now have, this implication I'm about to write down very much looks like solidity, except there's a plus added. M plus interprets N plus interprets K plus. And there's an M plus definable, meaning something which is definable here, between M and K. Notice it's not between M plus and K plus. If basically M plus notices, oh, my purely arithmetical part without the extra garbage is isomorphic to K, then M plus can already, then M plus, sorry, I shouldn't say already, then there's also a definable isomorphism between the arithmetical parts of the first and the middle model. So this is just like the definition of solidity, except that a plus has been added here up to here, but notice, and also here, but no plus has been added here or here, meaning we're just saying, if you just tell me the arithmetical part of the first and the last model are isomorphic, then I can work out that the arithmetical part of the first and the middle model are.
This was something that came up in towards the end of your talk last time, right? I mean, Matt, you magically somehow inferred, you deduced an isomorphism on the higher order stuff.
Right. So yeah. So
without
that,
having, assumed it, right?
Right. So that was actually a little different, but yes, you're right. In the model of Z2.
But that's precisely this type of consideration, though, right?
Yeah, here, yeah. So the interesting thing is that the proof that PA is generalized solid in this definition is exactly the same proof, really. You don't do anything differently than the proof of PA. So that's why, so G solidity in a way, and the only reason I thought about G solidity was I was trying to figure out how to get internal categoricity in a soft way from solidity. So the Hampkins-Frary argument shows that you get from from internal categoricity to tightness, but I wanted to do the other way around. So I can just show it to you in a diagram. I'm going to introduce this dotted implication notation for a statement A softly implying statement B. So this is softly in the sense of analysis, or to do, just the idea is that there's an easy argument to go from A to B, and of course that's a subjective description. So what happens basically is that before we look at internal categoricity, so this first arrow is just extremely trivial, and this one is just so-called a moment's reflection using the completeness theorem. Solidity implies tightness. So that's nothing new. I've just added this at the beginning, the G solidity. Now let me show you what happens with internal categoricity. So G solidity easily.
Can I ask you before you go? But I'm looking at the pluses, and I wonder if you erase some of the pluses, like maybe like the second or the second and the third, do you have something weaker or stronger? Do you need, in other words, do you need pluses? You need pluses for the first, for M, right? Because you need extra stuff to do interpreting. But the conclusions don't mention any pluses.
Yeah. This conclusion actually it uses basically the fact that we have a model of K. Basically, it uses the plus information because you see. Let me to answer your question. Maybe I can do it this way, Raman. This interpretation here could very well have used information that is in the plus part.
Right. Right.
And yeah, and the same thing, of course, here. So these interpretations themselves, in a way, and therefore this I eventually is going to would have to use them because the way I is concocted is basically from looking at what I0 is doing, but also what these interpretations were. So that's, I guess, my answer is that.
But the third plus is not used.
By the third plus, you mean which plus?
Over K.
This one?
Yeah.
Oh yeah, I see. Now the reason this is right, I guess this last one is not used. You're right. Let's see. Let me think for a second. Yeah, probably. Yeah, you're right. You're right. This one is not used, and meaning at least the way we both are seeing it right now.
It doesn't hurt.
Yeah. No, of course it doesn't hurt. It kind of keeps the symmetry, but you're right. Yeah, it can be simplified a little bit here. Yeah.
All right.
Okay. Now, so to summarize what's happening on this page, so the situation is actually kind of a little. So this first set of arrows was straightforward. In this situation here, the G solidity implies internal categoricity. This works smoothly for all theories with a soft argument. But this part is basically what I was referring to as being alerted to by Hampkins and Frary. So they noticed it for ZF, that internal categoricity implies tightness. So the same argument works for PA, even easier. And the same argument also worked for Z2 and KN. But the argument is specific to these theories, meaning I strongly doubt that internal categoricity for an arbitrary theory implies tightness for an arbitrary schematic theory, although it might. But
this was the arguments for set theory that were using things like Mostowski.
Yeah,
Or
so
am I?
actually, like, the argument that for example, the ZF uses is a class version of the Cantor-Bernstein theorem.
Oh,
So in PA, the class version is actually easy because we have a definable well ordering. So basically, I was thinking of this the other day. Cantor, as I think most of you know, proved the Cantor-Schroeder-Bernstein using the axiom of choice. He basically well ordered the sets involved, and then he could easily see that if A is embeddable into B and B is embeddable into A, then there is a one-to-one onto correspondence using the axiom of choice. But Bernstein and Schroeder managed to do the proof that we usually see in set theory courses that bypasses choice. Now in PA internally, we have choice because PA basically has the induction scheme. Every non-empty subset has a first element. So the proof of the class version of Cantor-Bernstein for PA is just really easy. But for ZF, you need this more sophisticated proof that we think about as Schroeder and Bernstein.
what do you mean class version? You mean second order vis-a-vis
No,
second
actually,
order?
I can be very specific. Suppose you're in ZF set theory, and then I give you two subsets of the universe, and I'm calling them proper classes because they're unbounded in the universe, X and Y. And if you have
And they're definable because otherwise you can't give them.
Yeah. That's exactly. Yeah. For example, I'll give you the class of ordinals as one of them, and maybe some other class as and then if you have definable injections from mutual injections, basically, then there is a definable bijection between them.
Yeah, that's fine, right? That's a theorem of theorem scheme of ZF.
No, it's a theorem. It's a theorem scheme if these were sets. So it's definitely meaning if A and B were sets.
What am I missing?
So what you're missing is that this is a definability of the bijection, because basically you have to be able to see that because it's a class version.
Yeah, but doesn't that's the whole point of the usual proof. I mean, okay, not that you can't do the Tarski-Knaster version, I know, but I mean the usual proof is when you talk about, chain sequences, finite sequences and continuing them and which ones are. So I mean, don't these things exist?
Yes. No, you're right. I mean,
there's a class of all those. That's all definable.
Yes.
There was early math overflow post about all that, and Joel cleared it, right? So
yes, this has been known for some time, and you're right.
So
you're
what's
right.
the issue?
If one knows the usual proof well, then it's easy to seem to be.
Well, that is the usual proof. What I give the Tarski-Knaster proof because I don't like to talk about natural number, but like maybe for this particular version of it, maybe you actually stoop to bringing in and there's maybe some discussion about what's predicative versus not, but that's a whole other.
Right.
But I mean, I thought you were saying that that's an issue here, but
no,
that's
it's not an issue here. But I was saying that in case because basically we're talking about theories that we understand, like ZF has a lot of coding, PA even has more well-behaved. But if you had an arbitrary internally categorical theory, then that part of the argument is not clear how to carry it out. This some general version which doesn't go through these intricacies of set theory. So this is pretty much where things stand then with internal categoricity. So at this point, I have material for the conjecture, but of course I'm going to go over time. So I have a suggestion that I do a third lecture down the road, because otherwise we would be here another 45 minutes, which is not a good idea at all. I mean, it's fine for me, but
I say it is an excellent.
Okay. So let's just end on this conjecture. So I think I've been mentioning this conjecture off and on, that PA is optimal in a way in a solidity and tightness. Now, so maybe the proper way of formulating this conjecture is to also add that there's no proper subtheory of PA that contains I delta 0. Maybe that would be kind of a more manageable one. Or maybe you insist that the subtheory is sequential. It can do a little bit of coding to kind of give it some oomph to begin with. But right now, every every theory we can think of that is a subtheory of PA that is also proper. And by subtheory, I mean deductively proper. So by subtheory, I don't mean just drop some axioms. I mean, you could drop some axioms and still, when you close under deduction, you might get PA back. The point is that if you have a deductively closed subtheory, and then the conjecture is that it's not tight or solid.
All right, like this non-existent theory that would correspond to the granular weight to ZF minus, which doesn't exist, but I mean, but some other, and maybe in some other setting, there could be a translation into such a theory.
Yeah. So for the case of ZF, actually, there is one theory for the case of ZF, which is Zermelo plus the statement that the universe can be stratified into V alphas. So that one actually is a very interesting subtheory of
where alpha ranges over von Neumann ordinals,
exactly,
or alpha ranges overall well ordered, because it's two different statements.
Overall for Neumann ordinals.
So you give yourself that much Mostowski.
Yeah.
You give yourself enough von Neumann ordinals.
Yeah. So you have full Zermelo plus this one statement which says basically V is equal to union of V alphas, basically. That's
right.
As alpha ranges over the von Neumann ordinals.
Okay, right. So the ranks axiom, I guess that's called, right?
Yeah, exactly. The rank sets, initial segments of the universe. Yeah. So that theory, so the available techniques and the most refined techniques are the ones that Hankins and Freire introduced. Leave that theory cold. They don't touch that theory. So this is
that one has Scott's trick. I mean, I don't know if that would be useful for you or not, but that or if the lack of Scott's trick precludes certain other.
No, but I think several people have been looking at this. You know, I looked at this. Hampkin and Freire looked at this, and then Freire and I mentioned this problem to at least 2 or 3 people who were really interested in this topic, and it's been quite resistant so far with the available techniques. Somehow a new idea is needed. Of course, the point is that to prove something is not tight or solid, you have to sometimes work really hard. So this is, I guess, what my third lecture would hopefully show, that it's one thing to show something is tight or solid. It's one thing to show that it's not. It's a whole different ballgame. And the available data that we have that I'll talk about in the third lecture basically would be that no finitely axiomatizable subtheory of PA is solid or tight. That's theorem 1. Indeed, if you look at the pi n consequences of PA for any fixed n, that also fails to be solid or tight. For example, PA pi 1 would be all the pi 1 consequences of PA, and that's not capturable by any I sigma n, because PA pi 1 would include the statements that I sigma 1 is consistent, I sigma 2 is consistent, I sigma k is consistent for any k. These are all pi 1 statements, which are all PA provable. But so this PA pi n is much larger than just as you allow n to range than just the I sigma n. And then a theory. So what's interesting about PA pi n is that you can kind of see, okay, there's some finiteness built into it, and this finiteness has to do with the fact that the consequences of PA that finite complexity, pi n. Now here's a theory that is not solid or tight, but its axioms are unbounded in complexity. You take any PA pi n that you want, and then you add the what's called the local reflection. Local reflection is a scheme, is sentences of the form, if phi is true, then phi is consistent. Consistent just in first order logic, meaning this is just the arithmetization of the fact that no contradiction can be gotten from phi, or phi is not provable from, sorry, not phi is not provable in first order logic, or phi ranges over arithmetical sentences. So this is the complexity of con part, of course, is it's always going to be pi 1, but this phi here is unbounded because it's ranging over arithmetical sentences. So this can be also shown to be not solid or tight. And then let me just move on to the third one. PA minus plus the full scheme of collection is also not solid or tight. So PA minus is the algebraic part of PA, is the axioms that are usually known as the axioms of non-negative parts of discrete ordered rings, finitely many axioms. So it's well known that PA minus plus the full scheme of collection is not full PA. Actually, the proof uses usually omega-1 like models, but there's a more refined proof that can be used to show that this theory is not solid either. And I think this is the 3 theorems I'll be talking about. Yeah, and then the rest of the talk would be the outlines of the proofs, which I guess in the next one it will be a little bit maybe more than outline. I think it's a good time to stop here. Thank you.
Thank you, Adi. I don't know if Atar is still there, but I'm here.
Yeah, looks like,
So somebody should say now, are there any more questions?
Are there any more questions?
You don't mention X, but the second, is that a typo, or is that you recover X? You're saying from ref?
No, this is a typo. Thank you. Yeah, this
Okay.
X. Yeah, actually, let's
That should
look
be
at
that.
yeah, let's look at this one because I didn't talk about
So
it.
the theorem of Kreisler-Levy is about I delta 0 plus X plus
Right,
1.
right. Actually, I think that.
Oh, okay, that
probably-
makes sense because you got to do your coding somehow.
Right. So when we have the global reflection, because they look so much alike, because so this scheme would be just for sentences,
Right.
and then this would be for formulas.
Wow. Oh, I
Yeah,
see.
for all x, phi of x, but this is also a scheme. So it looks like they're pretty much almost the same, but it turns out the previous one is a proper subtheory of PA, whereas this one, as observed by, Kreisel and Levy, gives you full PA. And as Adam is pointing out, this I delta 0 plus x was present here, and it was inadvertently dropped here. So just basically, this I delta 0 plus x is just there to give you enough coding machinery, and that's why it's there. In case you're wondering what is this x doing, it's just to be able to do well-behaved theory.
Those people who care to weaken that can
exactly
can go ahead, and that's not gonna.
Yeah.
Oh, now yeah. Now I remember why I remember that. It was a conversation at lunch I had with someone. I had forgotten why. Anyhow, weak theories.
I know the group, some logicians in Warsaw are also working on this conjecture. I'm not sure if they're trying to prove it or disprove it, but there are some at least some theories they've come up with, which are sub-theories of PA, which it's not clear whether they're solid or tight or not. So, but basically, any sub-theory of PA that at least we could think of, sub-theory in the sense of things that you meet sub-theories in papers or in texts, are the ones I just mentioned to you. If you can think of a sub-theory of PA, by the way, which I didn't mention, please do let me know. A sub-theory of PA which is not captured by the ones I just mentioned.
Thanks. Are there any other questions? And again, I apologize for jumping in and out of here.
Maybe maybe this is something of this. How about extensions of PA? How about PA and
right? So
Harris-Harrington.
Right. So extensions of PA
Steam.
typically are captured, meaning these extensions would have to be schemes then, right? Because if they're actually, yeah, thank you for asking that question, because the proof of failure of solidity for PA pi n, it actually shows something a little even better. It says that the true pi n statements, the pi n statements that are true in the standard model of arithmetic, so that's a larger theory than just PA pi n, is also for each n fails to be solid or tight. So those state,
So if there are finitely many of them, this is still.
this is still, But if you have some sort of, right, so it would have to be, I guess, statements that are true in the standard model that form an infinite set,
Mm-hmm.
in unbounded complex complexity,
In the same language as PA, so Presburger would be tight, wouldn't it?
Right, in the same language as PA, that's right. So this is basically, so the Presburger arithmetic, because it's complete, is automatically tight.
And
right.
solid?
And let's see. How would that? Yes, this is So going back to this theory, this conjecture rather. So Zach is pointing out that Presburger arithmetic, which only talks about plus, is certainly a subtheory of PA, and because it's a complete theory, it automatically is tight. It's not clear if it's solid, by the way. This is why this conjecture, I guess, needs to be kind of reminds me of this book, Conjectures and Refutations by Lakatos. So there is this sense that PA is minimally tight, and then whatever counterexample would come up with should be as silly as Presburger. Or how about this? You can even take the empty theory and say the empty theory, for example, is probably the empty theory is both tight and solid, because it can do nothing basically.
I think it is both tight and solid. It's anything.
So to give some meat to this conjecture, this should be a subtheory. I can now.
Dare I ask, in your formulation of things with the empty theories, do you allow empty domains?
I
don't
think you have to.
If you're going to go there, it's just something since I was never actually really trained in logic, it's something I don't really understand, but apparently all of the proof systems that we would teach our undergraduates, basically work under the assumption of non-empty domains. Any reasonable theory has that property anyway, so I shouldn't worry about it. But when I formulate set theory, I wonder if I need to call attention to an axiom of the empty set or not, because I don't do infinity until a week. So this has always disturbed me. So I mean, sometimes people say that it would violate, I would have to reformulate Gödel's completeness theorem, and why would I want to do that? And I think, but what's wrong with this theory where, I mean, either all the universal statements are true and all the existent, and then whatever. But anyhow, but that's not what you mean here.
I guess by empty, I just mean doesn't have any axioms.
But is for all x, does there exist x equals x? Is that an axiom of your theory?
So basically, just take the axioms, I should say, any additional axioms. So you have the axioms of first order logic.
Does that include there exists x equals x?
In some books, you're right. In some books, it doesn't.
Okay.
You're right. And I think it wouldn't make a difference in this situation. Okay. Yeah, but going back to fine-tuning this conjecture so it becomes a little more respectable, and thereby ruling out also Presburger arithmetic, is that if we add here no proper sequential subtheory, and a sequential theory is a theory that can code finite sequences, and Presburger is well known not to have any coding machinery in it. So the proper formulation would be which would rule out basically. Easy examples would be no proper sequential subtheory of PA. And to make that a little more maybe even more dramatic or more easier to state, no proper subtheory of PA that includes maybe I delta 0, if you want, to make it, to give it a little bit of arithmetical power, is tight or solid. Thank you, Zach.
Other questions?
I was thinking about Presburger too, but Presburger is complete in its own language, but it's not complete in the language of PA.
You're absolutely right. You're absolutely right. So if we think about tightness of, so I guess if we go back to the definition of tightness, the way it was defined was that a theory is tight is if you have any two extensions of that theory in the same language as you began with. Then as soon as they're bi-interpretable, then they are the same. They're the same, and under that definition, then Pressburger would be tight, because that is in the definition which at the very beginning of the slides, the U and V at work should be the theory that is basically we're claiming is tight. The U and V should be in the same language as what the theory that we're proving is tight. So to prove the tightness of Pressburger, we'd have to take U and V just in the language of plus and not allow multiplication. But going back to what you're saying, then let's see. So under that reading, then Pressburger is tight, but it's absolutely true that Pressburger says nothing about times. And
so is Pressburger in the language of PA still tight? I suppose.
Pressburger in the language of PA. Oh yeah, that's an interesting question. In the I don't know. So if you have two extensions of, so we have Pressburger, and then you have two theories that, but Pressburger in the language that allows multiplication. Yeah, maybe we think of Pressburger as ordinary Pressburger plus for every x times 0 is equal to 0, and therefore this version of Pressburger has times now. So some sort of silly Pressburger. Then if we extend it in two different ways, T1 and T2, and they are bi-interpretable.
I mean, probably trivially no, because you can probably do anything with the time. Well, or no, maybe I'm not thinking about this correctly.
You know,
it's not obvious that you can do things with the times in a bi-interpretable way that would, that are truly different. So
yeah, this reminds me. Yoko Vananen asked me when I had some contact with him recently. He was asking, could Pressburger be internally categorical? And don't know. So this question seems to be related to that, actually. And that might be even, I guess they're probably equally hard or easy to answer.
Is there any intuition on that?
I mean, on the one hand, Pressburger is such a well-behaved theories, and we have some sort of classification almost of these models. But interpretability in Pressburger, and I know it's been looked at off and on, but it's not that much known about it.
Mm-hmm.
But of course,
so Pressburger just means that you have two classes.
Yeah, I guess internal categoricity would be you have two pluses. That's right. You have two pluses, and the axioms of Pressburger.
And both.
Both. Now, of course, well, Pressburger is a scheme, right? I mean, you need these. It's not finite axiom, right? But still, it's almost finitely axiomatizable, and right? It's not clear how would the two pluses interact.
But you have plus and also the ordering. So
yes, you also have the ordering.
But if you go step down, if you look at Z groups, so
Yeah, and then if you're doing it right, then the ordering should be also different. Yeah.
You know, I'm sure it has nothing to do with the situation because the axiomatization is different, but I can't help thinking about there's this Randall Holmes didn't invent it, but he wrote something about this double membership set theory, where it's like you set it up. You're each one you're allowed comprehension with the other membership or something like that.
Yes, that rings a bell actually.
Eventually proved it was inconsistent, but it was a lot of work or something like that. So
right. Actually, that rings a bell. I also have
it's
seen
on his
that.
page. I haven't looked at this in years,
Yeah.
but it was weird. You had this weird restriction on coverage. It was like vaguely kind of like Ackerman. It's like you're not allowed to talk. You know, it's like anything which like didn't mention any formula which didn't mention the other symbol you could do comprehension on with this symbol or something like that.
I see.
Something like that. But you couldn't just set up Russell's paradox, you know, immediately, right? But somehow, anyway. Oh dear, I should dig that up. I'm sure it's still on Randall's page, but
yeah, I remember that actually from several years ago. Yeah.
I don't know if that would have any kind of interpretation about internal categoricity or not.
So basically, theories which don't have enough coding, you know, such as Pressburger, it's very hard to understand what does interpretability look within these theories. Of course, the fact that they have eliminational quantifiers tells you that at least you can get a handle on. So here's the catch: because they don't have enough coding, it's very hard to keep track of n-dimensional interpretations because for set theory and arithmetic, you know, basically everything is as good as one-dimensional interpretation. But if you're talking about interpretability in Pressburger arithmetic, you know, one should typically one allows n-dimensional ones, you know. And there, I don't know what the eliminational quantifier even looks like for n-dimensionality. Meaning, I'm sure there's a version of that, some sort of cylindrical decomposition theorem at work or whatnot. And the same thing, I guess, because I'm just mentioning cylindrical decompositions, you know, probably for the same situation for real closed fields and whatnot. What does interpretability look like in RCF? Because that quickly connects up to another whole branch of model theory. So I guess a little exercise maybe for me to ponder, so that maybe by the next time we talk would be I'll think more about Pressburger and also maybe even RCF or these complete theories that are to see what can one say about their interpretability in terms of these questions we're looking at, tightness and solidity. Sorry, tightness is easy because they're complete, but solidity.
Okay, any other questions or comments?
So it looks like the next two lectures would be Raman, and then I noticed Joel is speaking.
Yes. So let me stop there. So let's thank Ali again, and then and so next week we have Roman speaking at the later time at 7 p.m. New York time, and so we hope to see you all there. I'll stop the recording here.